warm welcome to the Big Data Conference and welcome in the machine learning track. And I will be your speaker. I am the host, Priyanka Sharma, and let me introduce you to the speaker. And first, let me tell you that wouldn't it be great if one can define and train your deep learning models without having to code? Well, I'm talking about a talk, a friendly introduction to codeless deep learning. And I invite a speaker, Kathrin Melcher, who is a data scientist at 9, also an author of 2 books, Codeless Deep Learning with 9 and From Excel to 9. I now invite Kathrin to present her talk.
Thank you very much for the introduction, and thank you everyone for joining my presentation today. As I got introduced already, my name is Kathrin, and I'm working as a data scientist at 9, which is a software company with the headquarters in Zurich, but I'm actually based in Germany, in the south of Germany, in Constance. And during my presentation today, I, on one hand, want to introduce you to deep learning and what is kind of the idea behind training deep neural networks. And on the other hand, I also want to show you how you can define, train, and deploy deep neural networks without writing any code. So let's get started. And I would like to start with the idea behind neural networks and deep learning. Why do I want to talk in addition about neural networks? Because neural networks are actually the basics behind deep learning, and deep learning are just deeper neural networks. So let's start really simple, and let's start with the simplest neural network we can think of. And that would be just a single neuron, so not really a network yet. And a single artificial neuron is actually inspired by a single biological neuron. And a single biological neuron has a cell body, and based on the inputs, the cell body decides whether the outputs are active or inactive. If we now model an artificial neuron based on this biological neuron, then we have again a cell body. And here the cell body also has some inputs, and based on the inputs, the cell body decides whether this neuron is active or inactive by using the weights and the bias and the function that the cell body or the artificial neuron has. How does the cell body now decide of this artificial neuron, whether it's active or inactive? To do so, it uses its weights, and it just multiplies the inputs with the according weights, adds the bias value, and then applies an activation function f. And this activation function could be, for example, a step function, where we say, okay, if this weighted sum is above a certain threshold, then we say, or the artificial neuron says it's active, and otherwise it's inactive. A single biological neuron as well as a single artificial neuron itself is not really clever, so it cannot solve complex tasks or do things that we can do with our brain. And therefore, we actually have a neural network, which is kind of many of these biological neurons or many of these artificial neurons working together. And here on the right-hand side, we see on the top a biological neuron where we see we have multiple biological neurons connected with each other. This means the output of one neuron is used as input by another one, and so on. And this idea is again used also in artificial neural networks, where we now combine many of these artificial neurons. And what we see here on the lower right is actually a really specific network architecture, which is called a feed-forward neural network, where we have an input layer for our inputs. In this case, this network could get 4 different input values. These are then used by the first hidden layer to perform exactly the same calculations as here. So they take the inputs, multiply them with the weights, apply the activation function. So we then know this one is active or inactive. And this information is then feed-forwarded to the next layer, where we perform again the same calculations, now with a different set of weights, again to decide which one is active or inactive. And then these values are used by the output layer to produce the output. And one important question that data scientists have to decide when defining the network structure is actually this activation function f, as well as how many hidden layers they want to use, and how many units these different layers should have. And what are kind of commonly used activation functions here? So I already talked about about a step function, where we say, okay, if the weighted sum is above a certain threshold, it's active, otherwise inactive. But actually, there are also other functions commonly used. So what kind of functions could a data scientist use? One function that was really popular in the 90s is the sigmoid function, which produces values between 0 and 1. And it has this S shape, as you can see here. And data scientists like to use this function as an activation function in the output layer if they have a binary classification problem at hand, because then the data scientist can interpret the output of our neural network as the probability for one of the two classes and then calculate also the probability for the other class. Later on, data scientists realized that using sigmoid function in the hidden layers is sometimes not working that good. And then they found out that a really similar function could be like the sister of the sigmoid function, which is the tanh function, actually improved the learning. And also this tanh function has this S-shaped function, but here we see now this function produces values between -1 and 1. And then in the 20s, so starting from 2000, data scientists and deep learning researchers realized that if they start to train really deep neural networks, this means networks with a lot of hidden layers, also there the training had they realized some problems during training. And the solution here then was this ratified linear unit to use this function in the hidden layers, and that improved the learning process again. The ratified linear unit just produces always the output value 0 if this weighted sum that we calculate with the weights of the cell body of the artificial neuron is negative, and otherwise it's just the sum of this weighted inputs itself. That was now quite a bit of theory. Let's try to apply this to a problem. And the problem I would like to solve now with a feed-forward neural network is a binary classification problem. And the goal is to train a network to predict whether someone is going to pass a certification or not. And here we have the example of passing the NIME L1 certification, which certifies you that you have basic knowledge with building NIME workflows. And let's say we have a data scientist joining the course, and he now wants to use some past data, which we have, where we know how many minutes someone attended the course and how many workflows a person has built and whether she passed or she didn't pass. And you can see also this data visualized here in the scatter plot. And now the data scientist uses this data to say, okay, I train now a feed-forward neural network to predict whether I'm going to pass or not this NIME certification. What kind of network architecture could the data scientist use? We have two inputs, the minutes attended and how many workflows a person has built. So the data scientist decides probably to use an input layer with two neurons. Then the data scientist decides to use one hidden layer with activation function tanh and two neurons, and then an output layer with just one output unit or one output neuron. And here the data scientist probably would choose the sigmoid activation function, because remember, the sigmoid activation function gives values between 0 and 1 and will allow our data scientist to interpret the output as a probability whether he's going to pass the exam or not. So let's assume that the data scientist has attended 170 minutes of our course and he built 8 workflows. Then what the data scientist can do, he can feed these how many minutes he attended and how many workflows he has built into our feed-forward neural network. Probably he would normalize the values, because that's what we normally do when we train feed-forward or when we train deep neural networks. And then he inputs these values into the neural network. And what the neural network would do is it would take these inputs, take the weights of the network and the bias function, the activation function tanh, and calculate the activation in the first hidden layer. And these values would then be used by the output layer to calculate the probability that a data scientist passes the L1 certification. Now the output is 0.013. This means we get a really low probability, or the data scientist gets a really low probability that he actually passed the certification. Now he probably starts thinking, how comes this? I actually attended most of the course, I built already some workflows. Why is this network predicting that he's not going to pass? And the problem with this network at the moment is that it was not trained yet. This means the weights and the bias values that we see here were just some random initialized weights. And therefore, training a neural network actually means to find weights and bias values for this network that lead to the correct predictions. How can we now train a neural network? To train a neural network, we actually need a labeled data set where we have our inputs and a true answer. Then what we can do is we can take the neural network with the initialized weights, feed our inputs through the network, and then we get the predicted value. And then we can tell the network how good its prediction was. Was it good or not? So we kind of need to tell the network whether the prediction was correct or wrong and how wrong it was. And therefore, we can use an error function to measure the difference between the predicted value and the true value and give this information back to the network. And in case of a binary classification problem, like the problem that we have at hand, we have two classes, pass or not pass, we can use, for example, the loss function binary cross entropy to measure the difference between our predicted and the true probability. When training a neural network, we then not use only one training sample to train the network, but we actually take many training samples, and therefore the error that we tell the network, which it is doing with the current weights, is actually the sum over the error that we make for each training sample. And the goal is then to find now some weights for this network that minimize this error function, because in the end, we want to have weights that minimize the error over all the training samples that we have. So how can we find now some weights that minimize our error function that our network is doing? Therefore, we can first of all look at an example loss landscape. Let's say, just so that we can visualize the process, we have only two weights, W1 and W2. And then this is the way how we could visualize this loss landscape, the error for each W1 and W2 combination. And then our goal would be now to find this W1 and W2 that actually lead to the global minima of this loss landscape. This means we want to find the W1 and W2 value that kind of lead to this value here. How can we do so? To do so, we can use the gradient descent algorithm or some flavor of gradient descent. And the idea behind a gradient descent algorithm can be compared with a mountain cyclist cycling on foggy conditions. So imagine you have a mountain cyclist going up the mountains, and now he wants to find down this way, but he can't see the valley anymore because it got really foggy. What could this mountain cyclist do? He could start at the current position where he is, and until he reaches the value, what he could always do is he could always look for the direction of steepest ascent, and then say, okay, then I cycle for 2 meters into the opposite direction. And he could do so until he returns to the valley, and then he could return the position maybe back to some other mountain cyclists. And the gradient descent algorithm does something similar. It also starts with the current position. This means with the weights that we currently have. And until we reach the minimum, it always calculates the gradient with respect to all weights. And this is actually the direction of steepest ascent in our loss landscape. And then the algorithm makes a little step into the opposite direction, which is then the direction of steepest descent. This means we update our weights by taking the current weights and taking the negative of the gradient multiplied by some learning rate eta, which defines that we just make a little step into this direction. And then the algorithm continues doing these steps until we reach a minimum. And then as the mountain cyclist, it also returns the weights. What is the gradient? Maybe a quick note here. The gradient is a vector with the partial derivatives with respect to all weights that we have in our neural network. We can also visualize this process in our loss landscape. So what the algorithm does, it always calculates the direction of steepest ascent and then decides, no, we want to make a step into the opposite direction, but just a small one. And it continues with this approach until it reaches the minimum. A step that is quite computationally expensive is actually the calculation of this gradient, which is the vector with the partial derivatives with respect to all weights. And an efficient way of doing this is the so-called backpropagation algorithm, which is used by different optimizers. But that's just something I want to mention, as this comes up often when you read about how to train neural networks. And if now our network is trained, so we have a good set of weights, and our data scientist uses this network with the trained weights, and it inputs again how many minutes he attended the course and how many workflows he built in the past. And the network uses this weights now with this inputs. Then we actually get also a probability of 96% that our data scientist who attended most of the course and built some workflows in the past is actually also going to pass the certification, what is also more likely. The loss landscape that you saw on my slides until now was actually a really easy way or a simplified way of a lost landscape. For real neural networks, this lost landscape looks much more complicated. And here you see an image of which I took from a paper, how a lost landscape can look like. And you can see that we have here a lot of local minimas. And to find here in this lost landscape actually some weights that lead to a global minima or which are actually a good set of weights for our neural network is much more complicated. And here an important parameter is actually how big do I make my steps. So the step size is here really important. And the step size is often also called learning rate. But luckily, we don't really have to take care of defining this manually nowadays because deep learning researchers came up with many different flavors of gradient descent where we have adaptive learning rates, which actually take care of choosing a good learning rate at any step when we train our neural network. And commonly used algorithms here are called, for example, ADAM, ADA delta, or ADA grad. When you train your first neural network, there are also some other important settings for the training, and two of them are the batch size and the number of epochs. When I introduced how the network is updating its weights, I said, okay, we take as a loss function the sum over all samples. This is actually quite computationally expensive. Therefore, normally, instead of using all training samples to make one weight update, normally only a part of the training set is used for each weight update. And how many samples are used for each weight update is actually defined via the batch size. And the other important setting option is the number of epochs, which is kind of the number of iterations, but it is the definition of how often each training sample is used. So it's not exactly the number of how many weight updates we do, but how often each sample is used. And as each sample is not always used for each update, it's not exactly the number of updates that we do, but the number of how often each sample is used. This means summarizing, when we want to train a neural network to solve a problem, what do we need to do? We need to define the network architecture that we want to train. This means we need to define how many neurons we want to use in each layer, how many layers we want to use, and which activation function we want to use in each layer. And in addition, we also need to define the training settings. Therefore, we need to define a loss function. We now use binary cross entropy for a binary classification problem. For other problems at hand, like for example, a regression problem, you might want to use mean squared error as the loss function. And we need to define the training settings. And one way of doing this is by using some code and using one of the libraries which are available, for example, TensorFlow via Python or Keras, which builds on top of TensorFlow. But what we did at NIME is we integrated Keras into NIME Analytics Platform. Maybe 2 words about NIME Analytics Platform. What is NIME Analytics Platform? NIME Analytics Platform is an open source tool that you can download for free from our website, which allows you to cover all the steps that you have in a data science cycle by not writing code, but building a workflow using a drag and drop tool. And I will show you the tool in a second and how you can use it to define and train neural networks. And yeah, that's what I want to do next. So this is how a workflow in NIME Analytics Platform looks like. And I now would like to switch to the tool to show you how you can define and train the network, which we just had in our example inside of NIME Analytics Platform. And therefore, we use here some data. I will quickly show you the data by doing a right click here on the CSV reader node, which we have at hand. So we have here the information, how many workflows the person has built in the past, and how many minutes he attended the course, and whether he passed or did not pass. And then we do here some pre-processing of encoding, for example, passed and not passed with 1 and 0, and creating here with the partitioning node a training, a validation, and a test set, and normalizing the data. What I would like to do now is I would like to just start defining our network, and therefore I first need an input layer. And if I type here in the node repository where I have all my nodes, Keras, then you can see already that there are many different Keras nodes. For each layer that you have in Keras, we have one node. And every network starts with an input layer, and therefore I first take the Keras input layer node. Then I need to define how many inputs do we have, and therefore I need to go into the configuration window of this node. Therefore, I can just double click and I say, yeah, we have 2 inputs. So I say our first layer, our input layer, has 2 nodes. Then we need the next layer where we had a dense layer, a layer that was connected with all the other inputs, where we use TANH. So I take a Keras dense layer node. I also connect it to the input layer node and then double click again to open the configuration window. And here I can say now, okay, I want to have a hidden layer with 2 units and the activation function, so it should be TANH. Then we need one last layer, which is our output layer, where I use another dense layer node. And I can connect it again to the other dense layer node. And here again in the configuration window, I can say how many units I want to have. And this time I want to use the activation function sigmoid, because we have our binary classification problem at hand. Then I can say again, okay, and now I defined the whole network structure I want to train. Next, I need a node that allows me to train the network, and that would be our Keras network learner node. And into this one, I can feed now my defined network, as well as the normalized training data and the normalized validation data. And here in the configuration window, I can now select which are my inputs, in which column do I have my target, and which loss function do I want to use. And then I can define all the training settings here. And for example, I could say I want to train this network using 100 epochs, and as optimizer, I want to use ADA. Then I can say OK, and I can execute this learner node. While this network is now executing, I have also an interactive view, which should come up in a second, which shows me how the learning process improves over time. And I will click now stop learning because I executed this beforehand. And then I can see how my loss or the accuracy of my network changed over the different epochs that I trained. So here I see the accuracy, and here I can see how the loss changed in red on my training set and in blue on my validation set. And then I can also apply this network to some new data, for example, with the Keras network executor node, which takes now as input the trained network, our test data, and then applies the network. And then I can also evaluate the model inside of NIME Analytics platform. And for example, with this example data set and the network structure that I defined here, I got an accuracy of 92%. And I could try now to improve this model by changing here, for example, the number of units that I use or adding more hidden layers. And with this, I want to switch back to my slides. But with NIME Analytics platform, you can not only introduce or define simple feed-forward neural networks, what we saw now, you can also define deep neural networks. And a category of deep neural networks that a lot of people refer to as deep neural networks are actually convolutional neural networks, which allow us to analyze images. And also here you can define networks, for example, for image classification, where you can read in images and then train a network to classify whether you can see, for example, ankle boots, t-shirts, bag, also on in the images. For this, we first need to think about how does a computer sees an image, and therefore a computer actually sees an image as a matrix, especially for a grayscale image where each pixel value is encoded with a number, for example, 0 for black, 1 for white, and a value in between for gray. And with this input, we can then train a network to detect different features in a CNN. And the idea of a CNN is then to use a network which has at least one convolutional layer. But the idea is to use many of the convolutional layers, where the first layer, for example, detects low-level features like edges, dark spots, and these kind of things. These features are then used by the next layer to detect mid-level features like eyes, ears, and nose. And then these features are again used by another layer to detect facial structures. Because I think I have only a few minutes left, I will skip some slides now, which I had kind of as optional prepared to introduce you also in more detail to convolutional layers. But what I would like to finish with is a small example of how this can look like then in NIME Analytics platform. So if you want to define a convolutional neural network in NIME Analytics platform, it works again with these Keras layer nodes that you define an input layer with the size of your input images And then you can have multiple Keras convolutional two-layer nodes, for example, to extract this hierarchy of features, and then use a Keras flattened layer, which takes these features and puts them into one vector. And then you can have a dense layer to kind of use these features to then calculate the probabilities for these different features. But you see, it's always the same steps. You can use the Keras layer nodes to define the structure that you want to train, and then you can use the Keras network learner node to define all the training settings, and then apply it with the Keras network executor. If you want to learn more about KNIME Analytics Platform, the open source tool, or deep learning with KNIME, we have 2 books. I last year wrote a book with my colleague Rosaria, where we introduced deep learning in detail and how you can do this in a codeless way. And we have our KNIME beginner slug, which you can download for free with the promotion code Big Data Values 0121 from our website, in case you want to get started with KNIME Analytics Platform and you need a bit of guidance or an introduction to the tool. And with this, I reached the end of my session. Thank you everyone for joining, and I'm happy to answer any open questions.
Yes, Kathrin, we have one question like, how do you know what step functions or loss functions in the landscape algorithm to use in the neural network design?
That's a really good question. I think I have a hidden slide for this. Oh, sorry about that. So that's a question that we get quite often, actually. I have a different slide. And we once created a kind of an overview to answer this question. So we see here the different hidden layers that I introduced, Sigmoid, Tannage, and ReLU, and they can be used for all types of problems in the hidden layers, whether it's classification or regression. But which activation function you use in the output layer and which loss function you can use together with this activation function in the output layer depends then on the problem at hand. For example, if you have a binary classification problem, then you can use Sigmoid in the output layer, like we did in our example, and then use binary cross entropy as the loss function. But if you have a multi-class classification problem, then data scientists often use softmax in the output layer with as many units as you have different classes, and then the correct loss function to use would be categorical cross entropy. And also for regression, you have different options. Normally we use the activation function is linear, is used in the output layer, this means in the last layer. And then you can use, for example, as loss function, the mean squared error, the mean absolute error. So it depends always on the problem at hand. And this slide actually gives you a nice overview. Do we have any other questions?
So I also feel, Kathrin, that it also depends on your experimentation. Like more trial and errors need to be gone into your training your model so that you get an understanding of what classification or what loss functions to apply, right?
For the loss function, it's quite clear depending on the problem that you have. For the network structure and which function you use in the hidden layer and how many neurons you use, that is more something of try and error. And what I normally do is if I start a new deep learning project, is that I look at some papers or some blog posts, which kind of give me an idea what could be an active a network structure that could work well. But the output layer activation function, how many neurons to use there, as well as the loss function, is normally predefined via the problem that you have at hand. Like, for example, whether it's classification, binary or multi-class, or whether it's a regression problem.
Another question, like how parameter tuning take place?
For this, you can either try out different parameters on your own. That's something that you don't want to do. But what we have as well in KNIME Analytics Platform is something that is called a parameter optimization loop, where you can define different setting options that you want to optimize. And then it kind of uses these different setting options to train different neural networks. And if you want to find here an example of how you can do so, what I can recommend is the KNIME Hub, which is KNIME Analytics Platform. As I said, it's an open source tool, and therefore there is a big community there. And the KNIME Hub is kind of the community place where people can share workflows. And here you can look then, for example, for parameter optimization. And then you will find many workflows where people used, oh, that's not a parameter optimization loop. Let's look for parameter optimization loop. And here you see then different examples where people use these parameter optimization loop to optimize different algorithms. And also in other algorithms, like for example, the decision tree or the logistic regression, you have different parameter settings. And what you always do here is in the loop start node, you define the different parameter settings that you want to test. And in the loop end node, which kind of measure you actually want to optimize. Is it the accuracy, the coins kappa, and so on.
Yes, we will provide you with the presentation that you don't have to worry about. Um, Another question, Kathrin, is that often my system, gets hanged when I try to run many epochs. So this is not a problem when I use KNIME, right?
Sorry, if you try many?
Epochs. When I train
If
the
you,
deep learning model, so often
mhm.
my system get crashed, it just hangs. So this possibly would be not encountered in KNIME.
No, that's something I've never encountered in I mean, I trained already quite a lot of neural networks for different use cases with text, with images, and that never happened to me. So that shouldn't happen. And if it happens, then shoot me an email or let us know via our NIME forum, because yeah, then we need to look into it. But that shouldn't happen.
So if you have any questions, please type them in the question and answers section regarding presentation. Yes, we have already answered this, that we will provide you. And rest, if you have any questions, you can reach out to the speaker's profile directly, and Kathrin will be happy to help any of your questions or doubts with. So uh, we'll wait for a few seconds. Let's see whether we get more questions. Yeah, we are waiting, guys. I think the talk was really very clear to them. Simple, sorted
That's
with
good.
KNIME,
That's good.
everything. Yeah, with blocks, you
But
can
I
just
but I
simply
do remember that my time was until 11:30, correct?
yeah, it just, we have still 12 minutes remaining. So it's, I just wanted one more thing to elaborate here, Catherine, is just these building blocks. You just put them into the software and connect it, and your neural network just gets, yeah, this one. So
Yeah,
so here I can also try and experiment with different things, right? So that would give me more knowledge about how does this really work. Actually, if
yeah.
I'm a starter, if I'm a suppose I'm a beginner and I want to understand it, so I don't have to like go to the Jupyter and go and typing
Yeah,
all these codes, right?
correct. Yeah, you can just drag and drop your nodes in and define any kind of network architecture that you might want to train.
And we also have documentation of the same, right?
Yes, yes. So you see here always on the right-hand side the node description. So whenever you select a node, you see here then the node description, and it gives you more information about what this node is doing, and what are the different setting options that you have in the configuration window. For the dense layer node, there is not much. But for example, I mentioned also the convolutional layers. So Keras convolutional layer. If I take this one, then you get in the node description detailed information about the different setting options that you have in the configuration window. So if I connect it to this one and I open the configuration window, then you see here you have the kernel size, the stride, so all the different setting options that you normally have in a convolutional layer, you can here define in with a graphical interface, and you have in the node description an explanation for the different setting options.
Answers my question. We have another question. It's like deep learning versus machine learning. When to use what?
Mm-hmm. So that's a really good question. Nowadays, everyone wants to use deep learning, or a lot of people want to use, not everyone, but a lot of people want to use deep learning. What I normally always say is start simple. First, use a decision tree, use a random forest to kind of get a baseline model, and then try to improve. And if this model is not accurate enough, then try to use deep learning to improve this model even more. And then also here, my tip is always start simple. Try with a simple network architecture and check that your model is not overfitting. That's a good question. How can you detect overfitting? Here, this view in the learning monitor is great, because if you see that your red line goes up, that's the performance on the training set, but your blue line on the validation set, like the data that is not used during training, goes down, then you see, okay, your model is already overfitting the training data. Then probably the network architecture that you took is too complex, has too many parameters, and you should try to simplify the network architecture again by removing, for example, some of the hidden layers. Yeah, so I always say, try first simple, go with standard algorithms, and then if they don't give you the results you would like to get, then try to use neural networks, or just try that to learn something new. That's also where I started with neural networks. I thought it's an interesting topic, and then I tried different use cases. Where they are really good is, for example, when it comes to image data. That's where they perform much better than standard algorithms. That's something where I like to use deep neural networks compared to standard algorithms, or also with sequential data, they are quite powerful.
Answers the question. I also have one connected question to this, Kathrin, that neural networks are often, what I've heard, that it is applied to a data set which is having thousands and millions of values. So is it not like using a lot of resource of my system when when I apply neural networks on simple use cases also? So
Yeah.
yeah.
Yeah, so first of all, to train neural networks, you really need a lot of data. Otherwise, they just overfit. They just learn your training data set by heart, and they are not trying to generalize. That's a problem that you can face with neural networks if your data set is not big enough. This means if you don't have a big label data set at hand, then I wouldn't recommend to use deep neural network either. And yes, training neural networks is quite resource expensive. What we have as well in NIME Analytics platform, or what you can do with Keras and TensorFlow, is to train a neural network on the GPU, if you have a GPU. And that's something you can do here in the advanced settings. So if you have a CUDA visible device, then you can also use GPU acceleration inside of NIME Analytics platform to train your neural networks.
Thank you, Kathrin. We have two more questions. Quickly, we'll take them. What is the advantage of NIME than Rapid Miner? In addition, can I add to NIME hyperparameters by own which are not included?
Mm-hmm. So maybe I split the question in two. Rapid Miner is another tool that also allows you to analyze data. What is the difference with NIME? NIME is an open source tool, for example. So the NIME Analytics platform, there is no limitation on rows that you can analyze. I don't know what kind of integrations or extensions Rapid Miner has, because I'm not working for Rapid Miner. I haven't worked much with Rapid Miner. I just had a look at it once. I'm not sure whether they have something like a Keras integration that allows you to define and train neural networks in that way as you can do it with NIME Analytics platform. About the hyperparameters, so how the parameter optimization looks like, you can actually really define on your own which parameters do you want to optimize. Is it the number of units, and then you define a minimum value and a maximum value, or is it the activation function, then you define the different values. So it's not that we have some predefined options what you can optimize and what you can't optimize, but it's rather that you can really freely decide which parameters you want to optimize.
One last question. Going codeless, it's something interesting. It's like going, yeah, going codeless is interesting, but behind that also code is used to develop such systems. So just curious about which language is used for this development.
So NIME Analytics platform is based mainly on Java. So it's an Eclipse-based application, and our developers use mainly Java to implement this. Just for the visualizations, we are using, for example, also JavaScript, because you can get nice JavaScript and nice visualizations using JavaScript libraries, like, for example, Plotly, which are then also interactive, which also allows you to build dashboards inside of NIME Analytics platform. But it's mainly a Java-based product.
We have taken a lot of questions, Kathrin. This was a really interactive session and such an insightful session. Wonderful session. Thank you so much. And I would also like to thank audience for their interest and attention. One good news, a short, quick announcement is that there's a good news for the attendees. who rate the session and leave comments, they will be awarded with ebook of their choice from our Knowledge Partner Pact, and the organization will contact the most active attendees after the conference. Do make most of this opportunity, guys. And yeah, thank you again for joining the ML track. Thank you, Kathrin.
Yeah, thank you everyone for joining, for all the nice questions, and enjoy the rest of the conference.